Hey, hi there. Welcome back to my YouTube channel. For those who are new, let me introduce you myself. I'm Cosmo, and in this video, we are going to talk about the uncertainty of the classical waves. In a previous video, we have seen the position wavelength uncertainty for the classical waves. But there is also another approach to the uncertainty of the classical waves, which involves the measurement of the time period of the wavelength. And to understand that, you first need to think about a device which can measure the time duration of the wave packet. Now we have seen in the previous video that the size of the wave packet is shown in the equation of the uncertainty relationship. But right now we are not measuring the size of the wave packet. What we are actually measuring is the time duration of the wave packet. So that means instead the size of the wave packet, the time duration of the wave packet will take the place of the size of the wave packet in the uncertainty relationship. For calculation, we can roughly estimate the time duration of the wave packet is one time period. With this consideration, when you try to measure the time period of the wave packet, you will realize that there is the uncertainty in the measurement of the time period. It is just because you have the difficulty in the defining the starting and ending position of the wave packet that we have also discussed in the previous video. Just like before, we can also describe this uncertainty as a fraction epsilon. So that means our uncertainty in the time period becomes epsilon t. Now we take the product of the duration of wave packet and the uncertainty in the measurement of the time period, which is the second uncertainty relationship for the classical waves. Okay, wonderful Cosmo. That means if we write this relationship in terms of frequency, which is the inverse of the time period, we get this relationship, right? No, actually, this is wrong. But how? Because this relationship indicates that if the uncertainty in the time is very less, which means the uncertainty in the frequency is very high. In other words, you can say that you can measure the time period precisely, but you can't count how much waves are passing in the given time period, which clearly makes no sense. But Cosmo, then how are we gonna include the frequency in this relationship? For that, we try to differentiate this equation, and by differentiating this equation, we get the relationship which shows that the frequency is directly related to the time period. And now we are going to use the most essential tool of the physics student: ignore and convert. We can convert this differential into finite interval, and as we just want the magnitude of the uncertainty, we can ignore the minus sign, and we have the direct relationship of the frequency with the time period. Now this relationship you can use in the uncertainty relationship to get the final result called the frequency time uncertainty relationship for the classical waves. So these are the uncertainty relationship for the classical waves. And if you want to know how this equation came up, click on the left side to check this out. And thanks for watching this video.